Okay, welcome back. We looked last time at rigid robot manipulators. Where Q was a set of joint angles, or more generally of joint displacements. Tau was the set of actuator torques. H, the inertia matrix. CQ dot, the set of Coriolis and centripetal torques. DQ dot, the friction term, the viscous friction term. And G, the gravitational torques. And we started looking at position control first, and we said if we're interested in controlling, let's say, a two-link robot in the horizontal plane, we can really get away with just using PD controllers if we don't care so much about performance, because PD controllers mimic springs and dampers that you would put at the joints, coil springs and coil dampers that you would put at the joints, and therefore do take the robot where to the fixed position where you want it to go. And to prove this formally, to take this idea of virtual physics implemented by the PD controller, we wrote conservation of energy. Which said that in this case, the time derivative of the kinetic energy was equal to the power input from external terms, and therefore to the power input from external torques, actuator torques, viscous friction, and gravity. So out of this conservation of energy, we could compute simply the derivative of a Lyapunov function, which was just the total energy associated with the robot and the virtual springs, and the derivative of that was the power dissipated by the virtual dampers. So that was, if we just were interested in Q equal QD constant. So for Q equal QD time varying, of course, this conservation of energy law was still true, but we said we would write it in a more technical form, in a matrix form, which would be then useful for the trajectory control derivation. So in matrix form, this same law of conservation of energy, which is still true, of course, was written in the form H dot minus 2c skew symmetric with an appropriate choice of C. So based on this, we said, okay, let's now consider the trajectory control problem. We have as a Lyapunov function candidate, we're going to just extend the ideas we had from the one-link pendulum. So we would look at not 1/2 of JS squared, but the equivalent 1/2 of S transpose HS. Now, while in the one-link robot, in the pendulum example, the J term was put in the Lyapunov function just to avoid dividing by J all the time. Here it becomes more important, more central, because here we have a whole matrix and its derivative and so on are going to be important. So if you want, this can also be seen as the kinetic energy of the system where you've replaced Q dot by S. Okay, so in a sense you seeing this in a kind of a different reference frame. And it gets in this form. And the main difference with the 1 degree of freedom case will be the fact that h is time varying. So we said if we differentiate v dot, we're going to get tau minus hq double dot r minus cq dot r minus dq dot minus g. And that's because we've used, I won't redo it again, right? We've used the fact that we have a skew symmetric h dot minus 2c to get rid of the h dot term by modifying this term, which from cq dot becomes cq dot r. Okay. So from there on, things should be very similar to what we did in the scalar case. So if you think of it, and you'll see examples in the homeworks, right? The gravitational terms, for instance, are equal to known functions, known trigonometric functions times mass property terms. Okay, so time constants. And similarly, let's say suppose this is a constant matrix D of friction coefficient, then you have again, a known vector, namely q dot, times a set of unknown constants, and so on. So all of these terms can be written in terms of products of known functions times unknown constants. Some of these constants are common to these terms. Some of them are specific, like the friction term. Okay. But so, of course, you can dump all these unknown constants in one big vector A, okay, which will contain all of these terms, and therefore write this whole term here as minus a known matrix Y, which is a function of q dot r and q double dot r, times an unknown vector A of constants corresponding to the mass properties and perhaps the friction coefficients and so on. So if we now trying to do this trajectory control for this robot, starting from arbitrary initial conditions, and so starting from arbitrary estimates of this vector A, for instance, we could initialize the estimates A at 0, then we can do exactly what we did in the scalar case, namely we're going to add to our Lyapunov-like function, which represents a quadratic measure of trajectory performance, right? Basically S square weighted in the right way. We're going to add to this a term which is going to be a quadratic term in the parameter estimation error, which, as you remember, will add exactly this term to the derivative. So if we now do exactly what we did in the scalar case, namely tau equal y times a hat. So in the scalar case, we had minus k times s, where k was a positive constant. Here we can more generally pick a symmetric positive definite matrix times S. For instance, a constant, or more generally uniformly positive definite matrix, just for simplicity, let's say a constant. So we see then, if we do that, we're going to get S transpose KdS with a minus sign coming from this term. We're going to get S transpose YA tilde coming from that term. We add this adaptation law, this extra term coming from the derivative of the parameter estimation error, and we choose the adaptation law to make this equal 0. which gives us exactly the formula we had before. And so if we combine this control law again and this adaptation law, then just as in the scalar case, as in the one-dimensional case, the system will tend towards the desired trajectory, starting from any initial conditions in the parameters and starting from any initial conditions on the state. So basically, once we've arrived here, then basically the algebra is exactly the same as in the one-dimensional case, and so we get that same result. Okay. So the combination of this control law and this adaptation law will give us simply v dot equal minus s transpose k ds, out of which we deduce exactly as if we did in the scalar case that v dot tends to 0 using Barbala's lemma, verifying v double dot is bounded, which implies that s tends to 0, which by definition of s implies that q tilde and q tilde dot both tend to 0. Okay. Any questions about that? Okay, so basically, same thing as in the scalar case with two modifications. The first one is that putting h here directly in the Lyapunov function becomes very central. Okay, it's not just to avoid dividing, multiplying by h inverse. Incidentally, h inverse is not linear in the parameters. Okay, h is, right? H inverse, is not product of known function times constant parameter. It's all mixed up, right? H is the product of known functions times unknown parameters. H dot, we get rid of this H dot term, which is an extra term we get here, using this conservation of energy, and from there on everything is pretty much the same. Questions about that? Okay. All right. So now, just like to make one last remark about these, right? So here we fundamentally use the physics of the system to choose our Lyapunov function and to basically simplify the algebra so that it becomes tractable. Notice that if we look at friction compensations, if we just focus a second on friction compensation, then we've treated friction pretty much the same as we treated gravity, right? So in other words, we treated it as an extra force, which was the product of known functions times unknown parameters, and we got rid of it, okay, adaptively. Now, if you think about it, this might have been a little of an overkill because, if you're interested in stability, friction might be a useful thing, right? So in a sense, here we said, well, we're going to throw away friction just as we threw away gravity, okay? Perhaps there's a better way, okay? So how can we see that friction is a useful thing? Well, it's kind of natural, just from the point of view of the fact it dissipates energy and so on, and so it's going to help things being stable. But algebraically, you can say, well, of course, remember S, which is equal, for instance, to q tilde dot plus lambda q tilde, or other versions, can always be written q dot minus q dot r, where we extract the q dot term and the rest we call q dot r. So it means that this term's dq dot that we have in the dynamics here, out there, right, or here, we can write it as dq dot r plus d times s. Okay? And so we see that basically our whole dynamics we could rewrite as hq double dot plus cq dot plus d not q dot but dq dot r plus g is equal to tau minus d times s, right? Just by replacing dq dot by this expression here, right? So that's the only thing I've changed, right? Instead of dq dot, I've put dq dot r, and therefore I'm left with my minus ds term here. Okay. Now, why did I write it this way? Because if you see this control law, right, it compensates for the dynamics as well as it can based on current estimates, right? And then it adds kd times s, right, where kd is a positive definite matrix. Okay. So in a sense, you know, this minus ds is very much like a kd times s, right, which we wanted to add anyway. Okay, it's a positive definite matrix times s. All right. So this is saying, you know, in dq dot, if you're throwing away dq dot, in a sense, you're throwing away the minus ds term, which was there naturally, and then you're going to add this term. So it seems a little of a waste. Okay. So what does this all mean? Okay, it means that we should think of just throwing away this term and leaving that term alone, okay? And if we do that, what does it mean? It means that we just have a different definition of y, right? Before we had h q double dot r plus c q dot plus d q dot plus g plus c q dot r, sorry, plus d q dot plus g was equal to y times a, okay? We can define a new y, let's call it y new, such that hq double dot r plus cq dot r plus dq dot r, I'll put some color, the only difference is instead of dq dot I have dq dot r, and this define a new y, okay? You know, some terms change in y because of that. All right? So we could redo the calculation, but I think you can reasonably imagine what is going to happen. So v is the same, right? We're going to choose tau the same, except, of course, in terms of y new. We're going to choose the adaptation the same, except, of course, in terms of y new. And what are we going to get for v dot? We could redo the calculation, but just think of it a second. Right? Everything cancels exactly the same way as before, except we've left this term here. Right? Everything else, all the algebra is exactly the same, right? So we've left this term here, it's just going to add to kd. And therefore, it's just going to add to kd here. Right? So we could redo the calculation, but we can already see what's going to happen, right? So what's going to happen is that we have S transpose, and instead of kds, we're going to have kd plus d times S. Right? So this still works, of course, because d is positive definite, but what did it say? It says that we've increased the gain kd, the effective gain kd, by the actual viscous friction matrix. All right? So in other words, we've increased the gain, but without increasing any gain, right? without, being sensitive to noise, perhaps, risking exciting our model dynamics and all these things, all these bad things about increasing gains, right? So in a sense, we've used the physics of the system, the natural damping of the system, to increase the gain. Okay, so for instance, we don't introduce any more noise in the system by doing so. Okay, so this gives us an effective KD which exploits the natural friction D term. Okay. So it's saying, well, we could have done it exactly this way, but we added one more layer, not of math, of physics, of saying, well, there's nothing wrong with friction, actually, if we're interested about stability, right? So we should be able to use it rather than fight it. Okay? And so if we do this, it means we modify y a little. Okay? And as a result, v dot becomes much more negative at any instant, right? Now, is this important? Well, it depends on the problem, right? Remember, this d was itself a function of q and q dot. Okay, so for instance, it could be a very small term. We talked last time about direct drive arms. Okay, a very small viscous friction. You have some electrical terms similar to that, but the mechanical viscous friction would be small. But think of, on the other hand of the spectrum, perhaps of things like underwater robots, right? So underwater robots, lots of drag going on, okay? And this is not a very good model of drag, but it certainly allows for quadratic terms in velocity and so on, right? So if you take an underwater robot, drag could be half of the dynamics, right? So it's very important to know whether you're fighting it as you do it here, or you're exploiting it as you do there, right? So here you're exploiting the natural viscous friction terms. Again, this d could be a function of q and q dot, while there you're trying to throw them away. Okay. So in practice, it can make a big difference. Questions about that?
So then for a general system, you would always prefer to use that kind of approach?
Yes, yes. So in other words, it's not because, this solves the problem, but, how optimal is it? And you can say, well, gravity, well, maybe I can't exploit gravity, okay? But friction, certainly I can exploit friction, so I can do even better, right? So yes, you might as well do this, okay? You might as well do this. Also, notice that actually, of course, this term, when you use an explicit dq dot r term in your control law, right? As a measurement, you only use position, right? Q dot r is q dot decide minus lambda q tilde. So you see that if you use q dot, you introduce perhaps noise due to the velocity measurement. Okay, you use q dot somewhere else, right? I'm saying in this term. While this dq dot r term doesn't have noise from velocity measurement. Okay, so it's always a nicer thing to do, right? And it makes sense from the physics because it's just saying, we're adding this term KD anyway, why not use the one which is already in the system? Okay. Okay. Any other question? So you see that as we get into these kinds of designs, right, it's not that complicated, and you can do rather powerful things, right? You can start the system anywhere with no knowledge of the parameters of either the loads of the robot, okay? And the thing converges very fast to the desired trajectory, okay? For instance, experiments on fast robots, you can have maybe 40 or so unknown parameters, and the typical trajectories, it would converge in about half a second or something like that to what you want. And don't forget also the reason it can be extremely effective is the remark we made on sufficient richness, the fact that it doesn't need to estimate the parameters correctly, right? It needs to estimate the parameters so that the task is done. Okay, so that's how it can be very fast and effective. Okay, so, but we see also, and that's nice in some sense, it requires more physical thinking about the system, right? To say, well, you know, this H is not any matrix, right? It's an inertia matrix, and its derivative has to do with energy, and this dq dot is not just anything, it's friction, it's dissipative, it should help us converge, okay? So we might as well use it, and so on. Okay? Questions about that? All right. So now you have in the book another example in section 9.4 of spacecraft control. It's very similar example. There you have loads, but you know, you're somewhere in space. So when you pick up the load, you also pick up the momentum of the load. Okay, and so you can adapt to that as well. Okay, that's an example which is discussed in section 9.4. So now what we're going to do now is switch gears and get back to more mathematical, purely mathematical things. And in a sense, this lecture and the next are going to be the most mathematical of the whole class, okay? So don't panic. But it's a set of interesting tools to understand about nonlinear systems, and it's also a very large area of research. So it's in chapter 6, and it goes on the general title of feedback linearization or feedback transformation. There's variations on this, and actually important variations on these kind of ideas, in particular questions of flatness and so on. But so we'll stick to basic concepts. So what's feedback linearization about? Well, the idea is extremely simple and very natural. The doing it is much more complicated, okay? But the idea is very simple, and it's something you know, everybody in this class should be familiar with, right? When you're trying to model, let's say, a mechanical system, right? The choice of coordinates is very important, right? What you use to describe your system, the reference frames, the coordinates, is very important. It's the same system, right? But depending on how you choose your coordinates, it may look more or less complicated. All right? So a general, if you want, question is, can we take a system which looks messy and show it's actually reasonably simple? Okay, so like a sheep in wolf's clothing, right? So take a system and kind of unwrap it and say it's very simple. Okay. Now you can think of it. It's easy to make up examples like this. Okay. You can take a simple system, do a very complicated nonlinear coordinate transformation, one-to-one but complicated, and the system will look very messy, right? But it's the same system, right? So the idea is, you know, suppose you're given a system that looks messy, can you kind of unwrap it? Okay. Or unravel it, if you want, depending on what you like to do. So that's the first intuition, if you want, which we know from just modeling, right? For the same system, what coordinates, what you consider as the state matters to the simplicity of the model, although it's the same system. Another way of seeing this, which gets a little more specific, is if you take a linear system, linear time invariant system, you know that under some conditions, basically controllability, you can do a state transformation of the system. Let me write it z equals z of x. In the linear case, it would be a linear state transformation. So that the new system could be written in a so-called companion form. Or controllability canonical form, which is 0, 1, 0 everywhere, 0, 0, 1, 0, and so on, all the way to 0, 0, and then 1. And then minus A0 minus A1 minus an minus 1, which are the coefficients of the characteristic polynomial of this system. Okay? So in a sense, what you have is you have a column of zeros. You have the identity matrix here of order n minus 1. And then at the bottom, you have, what defines the poles, right? So the coefficients of the characteristic polynomial. And there you simply have zeros and then 1. Now, if this vector z is written as z1, z2, zn, this transform vector z, what can we say? Are there things we can say about z1, z2, and so on, zn? Right? So this is a general result in linear control, right? You can take a system, you can transform it using a one-to-one state transformation, which in the linear case happens to be linear. And you can put it in this form. And what can be said about z1, z2, and so on? Well, if you think of it, this orange identity of order n minus 1, okay, tells you that, so let's say this, implies that, what's the first line? Okay, the first line is z1 dot equals z2, so in other words, z2 equals z1 dot. Okay. And the second line is z2 dot equals z3. So z3 equal z2 dot, in other words, equal to z1 double dot. And so on. Okay. So what does it mean? It means that basically this vector z, the first coordinate we can call z1, but the second one will be z1 dot, and the third one would be z1 double dot, and so on, all the way to z1 to the order n minus 1. Right? So saying that a linear system is in companion form, is in controllability canonical form, basically says that I've managed to find a state transformation, a one-to-one state transformation from the original system x dot equal ax plus bu to this transform system. It's the same system, right? It's one-to-one. So it's the same system. Such that the transform vector is in the form of some scalar function of time, and then its derivative up to order n minus 1. Right? That's what the first n minus 1 lines of this form say. Okay? What does the last line say? where the last line says z1 to the n, right? The derivative of this one, okay, is equal to minus a0 z1 minus a1 z1 dot and so on. Okay, so plus an minus 1 zn minus 1 plus and so on plus a0 z is equal to u. That's what the last line says. Okay. So this is what the first n minus 1 lines say, and this is what the last line says. Of this equation. Okay. So what is the last line saying, therefore, it means also that you've managed to take your nth order state equation and replace it equivalently, these are all z1s, sorry, and replace it equivalently by one nth order scalar equation. Okay. So you've taken this, you've done a state transformation, and in terms of the new state, in particular z1, which defines the new state, once you have z1, you know the entire z, right, obviously. In terms of the new state, you just have this nth order differential equation. All right? Which is why, incidentally, when we talked about robust control, we said we're going to consider systems of the form xx dot and so on, x2 n minus 1 and t plus u, for instance. And we said we would start with this nth order differential equation and then show things. And I said this nth order differential equation may come directly from the modeling, like F equal ma. Okay? But it's not entirely general for an nth order system, precisely because of this. So, for a linear controllable system, you can always do that. And feedback unionization or feedback transformation is wondering in general, for a nonlinear system under some form, can you always do this? Okay, so in other words, can you take some nonlinear system Can you take a nonlinear system, let's take a single input system to make things simple, and find a state transformation that puts it in the form of a linear system, for instance. And then, of course, you can put this linear system in companion form under some controllability assumptions. So if you start with this nonlinear system, can you transform it to look simple and linear? And of course, once you've done that, you can further transform it to look like this companion form. And therefore, you can take your original nth order nonlinear system and transform it into your original, state equation, n-dimensional, and transform it into one nth order scalar equation, scalar differential equation. That one, right? So that's the question, right? So that's why, in a sense, the question is the same or pretty much the same as what we were saying originally. When we looked at these robust control questions, we said, how general is this form? Okay, and we said the main thing about this form is that the state is something and its derivatives. Right? So the question, which is what this chapter is about, and again, you have history of the ideas in this chapter at the end. The question is, starting in a system like that, can we do a state transformation such that the new state is of the form zz dot z to the n minus 1. Okay. And more generally, can we take a nonlinear system and do a state transformation so that at least it looks simpler? Maybe not very simple like this, but simpler, right? Are there obvious things you can do to a nonlinear system that make it look simpler? It's the same system. Okay? So these are the questions, okay? And we'll see that they are extremely specific answers to these questions, necessary and sufficient conditions for these questions. Okay? We'll see that some of the practical aspects of applying these results, still create difficulties in some cases, okay? But so we'll see it's not obvious to apply, but it gives you, precise results basically about the structure of nonlinear systems. So now here we're not considering robustness at all, okay? Remember we said if we have a system like this, or maybe to be consistent in our notations, if we had a system like z to the n equal f of z dot z to the n minus 1 t plus, let's say, u. We said if we have a system like this, or maybe even plus bu, right? Maybe. We said if we knew everything about f and b, we would not need robust control, right? We could just call this entire quantity v, right? So that the new equation is z to the n equal v. We could do whatever we want with this equation. It's a linear time invariant equation. And then at the end, we could recompute the corresponding u. Okay, u equal 1 over b times v minus f, right? So if we knew exactly f and b, that's what we could do. We would not need all this robust control business. But as we said, of course, we don't. Okay, we don't. That's why we do all of this. Okay, but the flavor of this chapter is very much going to be this. Okay, in other words, assume we know everything. Once we are here, we're done. Okay. Okay. So in a sense, it's very complementary to what we said about robust control. Okay. It starts with perfect knowledge of the system, tries to transform it, and leaves to somebody else the question, well, what if there is uncertainty in the system? Okay, so it's very complementary to robust control. But it's more complicated than robust control. That's why we do it now. Okay? But it's two things that go together. Okay. So now there's two general classes of techniques. So we'll first kind of introduce them and then go into the math. And going into the math will be mostly next time. So suppose we have a system of this form. x1 dot is equal to minus 2x1 plus ax2 plus sine x1. x2 dot is equal to minus x2 cosine x1 plus cosine 2x1 times u. All right? So this is your system. and you've been asked to design a controller for the system, for instance, to make the state go to 0. Right? So here what we're going to do is try to solve this question. How do we get a state transformation that makes the system look simple, linear in this case? We're going to solve this question by hand if you want. And then, because you know here the system is low order enough that it's easy to do so. So what are we trying to do? Well, we're trying to transform the system into this form. But of course, we know it's good enough to transform it into a linear form, because once we have that, we can certainly get the companion form. Okay. So basically, we're trying to find changes of state variable such that the new system in these variables is just linear. Okay. And we're completely free to do whatever we want. Because we assume that we have an exact model, okay? And so it's just an algebraic transformation of the model. So one idea which could work nicely is to say, okay, we have minus 2x1 plus this nonlinear term. A is a constant. Put this constant here just to make a remark later about robustness, okay? So A is just a constant. So let's say we have this first equation. It's not linear, right? But suppose we let z1 equal x1. Then if we define this to be z2, now it's linear. Okay, we haven't done much, right? So z1 equal x1, z2 equal sine x1 plus ax2. So this first line becomes, what does it become, the first line? z1 dot equals minus 2 z1 plus z2, right? I haven't done anything, right? I've just called this nonlinear term, which was in the middle, I've just called it z2. Okay? So this doesn't sound like very deep at this moment, right? I've just said, I don't like this term because it's sine x1 plus ax2, I'll just call it z2. Okay? Now, of course, you still have the second equation. So what are we going to do? We're going to take this z2 and compute its derivative, right? So that's very easy, right? It's the derivative of this. We plug in back this equation, okay? And so if you do the algebra, which is very simple, you'll get that z2 dot is equal to, let me write it here, minus 2z1 cosine z1 plus cosine z1 sine z1 plus a cosine 2z1 times u. So that's the z2 dot equation. And I still have the z1 dot equation, which is z1 dot is equal to minus 2z1 plus z2. Okay? Everybody follows what I did, right? I just took this equation z2 equal. I just differentiate it and compute the terms, right? I have a term in x1 dot, I have that. I have a term in x2 dot, I have that. I just replace. Okay? Incidentally, we did this. Is this a one-to-one transformation between x1, x2, and z1, z2? Absolutely, right? z1 is equal to x1, okay? And so once we know x1, and you give me x2, I can give you z2, and the other way around as well. Okay? So if you give me z1, I give you x1. And if you then give me z2, I can give you x2. Okay, so it's a one-to-one transformation. All right, so we've taken this system and we've replaced the first line by this. We've replaced the second line by that. You might say, well, the second line looks complicated, but of course we're assuming that we know everything about the system. So this entire quantity we're going to call V. Right? It's a new notation, which is the control times something plus something known. In all of what I'm saying, assume we measure the state, okay? The original state. So where are we now? The same system is now written. z1 dot equal minus 2z1 plus z2. z2 dot equal v. Right? And so from there on, of course, you can design v to make z1 and z2 do what you want. What do you do once you have v? Because v is not the real control, u is the real control. Well, you just have v equal to this, so u equal 1 over a cosine 2z1 and so on, right? You can just solve this equation, right? Given v, you can compute u. All right? So design v. Compute u equal 1 over a cosine 2z1 times v minus a bunch of things. Okay? So you see, we started with a system which look a little messier than from what we used to, okay? But, you know, still second order. We said, okay, well, let's pick x1 equals z1. That's not very creative. Let's look at z2. Well, we'll call this z2 because then the first line is very simple, and we do have a one-to-one transformation. Now we have to wonder, what does z2 do? Well, we compute z2 dot from the definition of z2 in this differential equation. And this whole quantity we just call v because we know if I know x1 and x2, if I measure x1 and x2, I can compute z1 and z2. And therefore, given v, I can solve for u. Okay? So here we kind of did by hand, you know, what we said is the big question, okay? Which is, how do we find a one-to-one transformation that makes the system into a simple linear form? A few remarks about that. U equal 1 over a cosine 2z1 means there's a singularity when cosine 2z1 equals 0, right? Because you have this 1 over cosine 2z1, okay? But that's, you know, it doesn't say, you know, the method is bad in the sense that because the singularity was already in the real system, right? It's just whatever the control input does, it goes through cosine 2z1, right? It's, to x1. So if that happens to be 0, then of course you have a singularity. Okay, so the singularity is just a reflection of the fact, you know, you have this nonlinear dynamics and this term here, which comes physically from the modeling. Okay. So that's the first point. So cosine 2z1 equals 0, by the way, is the same as cosine 2x1 equals 0. You measure the state x to compute the state z, which is used in V, in the design of V, okay? So here we assume that this is all correct and we have this constant A, which is known. You see that once we transform the system, this constant A appears both in the state transformation, in other words, in how to go from x to z or back, and in the choice of control law, 1 over A times. Okay? So you can see that immediately if you had some uncertainty on A, it would mess this up, considerably, right? So this is based on having a precise A, A is used both in U and in the state transformation. Okay? So you see, that's why I'm saying, these are two separate problems. One is saying you have this exactly known system, how to transform it to make it look simpler. Okay? And then there is the question, suppose you have uncertainty on the system, how do you deal with it? Except now there's an extra question. You have uncertainty on the system. How does it fare through these transformations? What does it become? And then you have to deal with it in this form. Okay. All right, so that's why I was saying, these are mathematical results about the structure of systems, right? They say you have an exact model. This is how you can transform it, but the transformation depend also very much on the assumption you have an exact model. Okay? And if you don't have an exact model, then you have to wonder how does imprecision of your model translate in terms of imprecision on the transformed system and the transformed state. Okay? All right. Questions about that? So I'm not saying, and therefore you know how to do this. We'll quote theorems and so on. I'm saying on this simple example, it was reasonably straightforward to achieve what we want, okay? Namely, transform the system into a simple linear form out of which we can then do control. Okay? It requires a state transformation. Incidentally, it requires an input transformation too, but that's the easy part, right? In a sense, you just call this the input and you're done. Okay, so that's one example, if you want. And the general theorems will quote, will say, whether this can be done for a given system. And of course, they will still have the same limitations linked to robustness, same potential limitations linked to robustness. Okay, so any questions about that? So this is called input state feedback linearization. You've transformed the whole state into a new state where the corresponding dynamics are linear. Okay? So that's why it's called feedback linearization. Okay? It's not linearization in the sense of linear approximation. It's linearization in the sense that the transform system is linear. Okay? All right. Now, there's another point of view on this, which is called input-output feedback linearization. And in a sense, it's saying, okay, suppose you start with a big nonlinear system, and you have one variable, for instance, you'd like to do trajectory control on. It has the flavor, if you want, on Google search, you have this thing in quotes, say, I feel lucky, right? So it has this flavor of saying, okay, well, perhaps if you take that variable that you're interested in, the one you're really interested in, it happens to be Z1. So that if you differentiate it, you keep differentiating it, then at the end of differentiation, you'll get exactly the control input, and you'll have done what you want. So so the idea is, you have a variable interest, for instance, you're trying to do trajectory control of this variable. You're going to say, well, is it possible that this is precisely a Z1 that would work? Okay? Now, of course, in F equal MA, it's already the case, but if you don't need all of this, right? In F equal MA, it is, right? But that's the idea. Okay, so let's see an example. Okay, so you have this system, and you want to control x1. Well, so let's try it, right? You want to control x1. We're saying, well, we're going to see if this x1 could give us a good z1. By the way, perhaps it's not unique and so on, right? So could give us a good z1. So what are we going to do? Well, we're going to compute. We're going to let z one equal x1. And we're going to differentiate that. Okay, so that will give us z1 dot equal just this first equation. Okay, so sine x2 plus x2 plus 1x3. Fine. So what about z1 double dot? Well, you have the derivative of all of this, right? And in particular, in this derivative, you'll have an x2 plus 1 times x3 dot, right? And so therefore, you'll have an x2 plus 1 times u. So in other words, what you get is z1 double dot is equal to x2 plus 1 times u plus a bunch of other things, of other known things, right? Everybody understands this, right? z1 dot is equal to this. It's just the first equation. You differentiate it again. You have the derivative of this, right? And the derivative of that. That contains in particular x2 plus 1 times x3 dot. And therefore, it contains x2 plus 1 times u. All right? Now, Well, you might say this is great, right? I've differentiated this z twice, and I can find u. Now I know I can give names to things, right? So I'll just call it v. Now I have z1 double dot equal v. I can design v to make z1 do anything I want. Right? Okay. You've taken your variable, you differentiate it. At some point, the control appears. You call the whole right-hand side v, and you're done. Or are you? Well, suppose you had a very big linear system, right? d over dt of z, right? Perhaps. Well, not call it z, let's call it x, not to confuse things. Suppose it was, I don't know, 1, 0, 3, 4, minus 7, 0, plus 1, 0, and other things times u, and then other terms. Huge system, maybe, or maybe just big system. Let's say 20 variables, and you have this, and you're interested in controlling z1 or x1. Sorry, x1, the first component of x. Suppose you apply this method. Well, you're going to say, let's pick z1 equal x1. Let's differentiate it. So I have the first equation. U appears. Call the whole right-hand side v, and that's it, right? I've completely forget about the other 19 equations. I design things based on that. That's what this is suggesting, right? If you stop here and say, well, and therefore I'm done, Clubmed is calling or whatever, right? In that case, holidays calling, and therefore I'm done. You doing exactly what you would never do here, right? You would never say, well, you know, I have 1 appearing in B, and therefore I can consider only the first line. So, what is it saying? It's saying that once you've done this, there's a leftover dynamics, right? But there is a leftover dynamics here of order 3 minus 2, in other words 1, right? We have third order system and we have this second order thing, right? Also subjected to the same u. So if you do something like this, you differentiate until you find a control, then you still have to wonder what happens to the leftover dynamics once you have your control. Okay. Now, still, one more positive way, if you want, of saying this is saying, well, at the very least now, the first 2 equations are simpler. Right? By picking the z1 and so on, you still have a nonlinear system. You don't stop here, but at least the first 2 equations are simpler. I just have a, you know, z2 double dot equal. Okay. So what we'll see with some technical caveats, but what we'll see is that indeed this I feel lucky quote way does work if indeed you're lucky, right? In other words, if it takes exactly n differentiation to find the control input, then indeed you'll have exactly what you want, and you'll have gotten it in a very simple way. Right? Suppose this wasn't what happened. Suppose Z1 double dot was yet something which doesn't contain U, and I need to differentiate a third time to get U. Okay? Then that would work actually. Right? So, in a sense, therefore, this question of is it possible to take my system and put it in a linear form with some technical qualification is more or less equivalent to saying, is it possible to take my system and find a scalar function, z1 of t, such that if I differentiate it n times, I find for the first time the control input. So that's, is it possible to find a scalar function z1 of t such that it takes exactly n differentiation for the control input to show up in the equation? All right? Now, so here actually a lot of developments in this line of work were about trying to extend to general nonlinear systems, or more general nonlinear systems, systematic techniques as what you have in linear systems. So to get a little more of a handle on that, one way is to just look at what are we trying to do in the case of linear systems, okay, as we did a little here. And maybe take a very simple example. So this is example 6.4 in the book. So suppose that we have x1 dot is equal to x2 plus u, and x2 dot equal u. And we want to control x1. Well, we want to control x1, right? So since x1 dot is equal to x2 plus u, using this quote technique, right, it's easy enough. So let's say we want to control x1 to 0. Okay, so we have x1 dot is equal to x2 plus u. So we can pick u equal minus x2 minus x1, let's say. And that would give us x1 dot plus x1 equal 0. Okay. So if I have this system, right, x1 dot equal x2 plus u. If I choose u equal minus x2 minus x1, then of course I get a very simple linear differential equation that let x1 go to 0. Okay. So that's u is going to this first equation. But it's also going to the second equation, which is x2 dot equal u. And there it will imply that x2 dot plus x2 equal minus x1. Right? So you've chosen u based on the first equation. But of course it applies to the entire system, so it also goes in the second equation. And that's what we get. Right? Everybody understands, right? We design u based on part of the system, and we're saying, oh, by the way, the same u applies to the whole system, right? So let's see what happens. So the system being simple enough, that's what happens. So x1 tends to 0. What about x2? Well, so does x2, right? Because it's just a filtered version of minus x1. So actually, here it's fine. Okay. Here, just looking at the first equation was fine. It happened, but it also worked for the second one. Or at least nothing bad happened in the second one. We didn't care really about x2 going to 0. We just wanted x1, let's say, to go to 0. But if x2 had gone to 6, that would have been fine too, right? Okay, so it happens to be fine. So suppose we take now an other system which has the same first equation, but the second equation is x2 equal minus u. So we still have, of course, x1 dot is equal to x2 plus u, which will give us x1 dot plus x1 equals 0. Because we'll choose the same u, right? Because we have the same first equation, same u. But the same u now is going in the second equation, right? Which is x2 dot equal minus u. So it gives us x2 dot minus x2 is equal to x1. And so this implies that x2 is unbounded, right? For any non-zero initial conditions. Right? So you've designed your system based on one equation. The second equation blows up. You might say, who cares? I cared about the first equation, right? But of course, if it blows up, it also means, you know, it blows up out of your model, right? The system burns or whatever, okay? Right? If you think of it, this is very similar to questions of observability, right? In a sense, you've looked at only part of the system and you forgot about the rest. Okay? So here we are in the very, very simple linear examples. In this case, it works. In this case, it doesn't. All right? Any idea what's the difference? How we could describe the difference? Well, it's very easy to check that if you look at the transfer function, so here s is the Laplace variable. If you look at the transfer function, x1 over u here, you're going to get s plus 1 over s squared. Well, if you look at the transfer function x1 over u here, you're going to get s minus 1 over s squared. So just from the point of view of undergraduate linear control, what's one of the key differences between these two systems? Well, here it has a 0 in the left half plane, and here it has a 0 in the right half plane. So here, in other words, it's minimum phase. And here it's not minimum phase, otherwise creatively known as non-minimum phase. Right? So intuitively, this kind of makes sense, right? Because what is minimum phase saying? It's saying that the inverse system is stable. So going from x1, if x1 behaves, so will u. While non-minimum phase is saying, well, if x1 behaves, you don't quite know about u because the inverse system is unstable. right? So what we'll see, because it will tell us more about the structure of the system in general, that for linear systems, not for nonlinear systems, but for linear systems, this result is general. In other words, for linear system, if you just consider part of the system corresponding to a minimum phase transfer function, then actually it's okay to forget the rest. Okay? But for nonlinear systems, it will be much more subtle than that. So in a sense, it will just help us put the system in a simpler structure, but we won't have something just as easy as that. Okay? So that's what we'll see next time.